So in this video, I've got three integrals for you to calculate. Have a go at them with pen and paper. This one is a definite integral, these two are indefinite, and I will give you full solutions in a couple of moments after you've worked them all out. Okay, welcome back. Let's look at them on the next three slides. So all three of the integrals in this video can be calculated by inspection. Let's look at the first one. So we have a power of the sine function multiplied by the derivative of the sine function. That means you could, if you wished, make a replacement, and you could say, well, let u equal sine of phi, you'd have u cubed. This is a derivative, and you could turn this into the integral of u to the power of 3 with respect to u, but there's no real need to do that. All you can do is say, well, I think this is going to be something like this to one more power, so you leave a gap, and you write the sine of phi to the power of 4, we've increased the power by 1, and then you just say, well, if I was to differentiate this, I'd pull a 4 in front. I don't like that, because there's no 4 here. Easy to fix, I'll put a quarter in front. And then I would reduce the power by 1, I'd have sine cubed. Excellent. And then from the chain rule, I would multiply by the derivative of sine, and that is cosine. So that's exactly right. You can pause, check it again in your heads. If you differentiate this, you get exactly that. This is to be evaluated between the upper limit of pi over 6 and the lower limit of 0. So we have a quarter sine to the power of 4 of pi over 6 minus a quarter sine to the power of 4 of 0. Sine of 0 vanishes, so that term is just going to vanish. There's no problem with it. What about the upper limit? Well, the sine of pi over 6 is a half, and this is one that I don't think you ought to need a calculator for. And if you can't remember how to work it out, you draw an equilateral triangle, drop a perpendicular. The angles in an equilateral triangle will be pi over 3, but if you've bisected it, as I have here, this is pi over 6. So if I choose the length of the side of the triangle here to be 2, I'll have 2 here, and this side, because it's an equilateral triangle, would have the same length, but I bisected it, so this is 1. So you can see immediately that the sine of pi over 6 is a half. So we have a half to the power of 4, and 2 to the 4 is 16. So in the denominator here, we have 4 times 16, and that is 64. So our answer for the integral is 1 over 64. Okay, let's look at the next integral. So the second integral may initially look a bit horrible, but what we recognize is that outside here we have got the sine of theta, which is the derivative up to a minus sign, hence the approximately, of the cosine. So you could imagine performing a change of variables, a substitution, saying, we'll say this is sine of u, and then this is more or less the derivative, and therefore we could rewrite it, blah, blah. I think it's much easier just to guess the answer and write it down, so we'll perform it by inspection. And the integral of sine is cosine. You're certainly not going to change the argument, so it's going to be the cosine of theta. There'll be some integration constant, and I've left a space in front in case something is needed. So what happens if we differentiate this? Well, if you differentiate this, you're going to be using the chain rule. Derivative of cosine will be minus sine of the same thing, so minus the sine of cosine of theta. That's that up to a minus sign. But then, so I'll put a minus sign perhaps just to be safe. And then from the chain rule, we're going to have to multiply by the derivative of this argument. So we're going to multiply by the derivative of the cosine of theta. And that's again minus sine of theta. Sine of theta we like, and that minus sign we don't like, so we'll put a plus sign in front. So there are two minus signs when you differentiate here, but they will multiply together to give plus, and that gives exactly this. So pause, do it again in your head. Minus sine of cos theta multiplied by derivative of that minus sign, minus is plus. So yes, that gives us exactly this. This integral is correct. Let's look at the third example. In our third example, we've got a power of the secant multiplied by a tangent. And the key fact that I'm remembering is that the derivative of secant is secant times tangent. So 1 power of secant times tangent is the derivative of secant. So our integral is secant times the derivative of secant. I've pulled out one of these two powers and multiplied it here. So we could again make a change of variables, but we can just write down the answer. This is going to be secant to the power of 2. There might be a number. Let's leave a little space. What happens if we differentiate this? We'd pull a factor of 2 in front. We then have secant of theta, because you reduce the power by 1, and you would multiply by the derivative of secant, exactly this, secant times tangent. So that would give us the initial integrand, except that we'd have a factor of 2, so that's easy to fix. We just put a factor of a half in front, and that is our result for the integral. Now, supposing we'd changed the power at the beginning, supposing we had here, let's say, to the secant to the power of 20, what would change? Well, we've still got one of those secants that we could pull out and multiply by the tangent. So our integral, this is now secant to the 20, would be secant to the 19 times the derivative of secant. So one of those secants times the tangent is that derivative. And then again, we'll just say, well, this is going to be secant to the 20. And if we differentiate secant to the power of 20, you'd pull a 20 in front, reduce the power by 1, secant to the 19, times the derivative of secant, so secant times tangent. And we don't want a 20, so we just have to put a 1 over 20 there. So you can see this is nothing special about the initial power. It's just if you've got some power of secant times a tangent, you can do something like this. And I think integration by inspection is, well, it's my favourite method of integration, and it just comes really from practicing the chain rule a lot. Okay, with that, I'll stop this video.